Organizing. And as part of our first webinar, we have chosen to talk about two very essential technologies that are spearheading the water sector. We will be first talking about desalination and then about advanced oxidation processes. So with that, let me first introduce our very esteemed speaker, Mr. Amir Basha, who is the CTO desalination from VA Tech Wabag. He has graduated from Madurai Kamraj University and has more than 3 decades of experience in the desalination sector, not just in India, but also in the Middle East. He has worked with prominent entities within the sector and is now spearheading projects with VA Tech Wabag. One of the very famous projects that we all have heard about is the Nemali project, the 110 MLD desalination plant at the Chennai coast, which Mr. Basha will tell us more about during his talk. He has more than a decade of experience, not just operating it, but also spearheading and pioneering operations within desal plants. And we are very, very honored to have you, sir, today. And we're looking forward to learning from you more about desalination as a technology, opportunities and challenges in the sector. And our audience is mostly industry experts as well as young water professionals in the water sector. So, with that, sir, I hand over to you and we look forward to your talk.
Thank you, Sudeep. Good evening to all. First of all, I would like to thank you for giving an opportunity to present. And I assume that since all are water professionals, I think all are familiar with desalination and seawater reverse osmosis, so that I need not go with the startup introduction and other thing. I will straight away go because the duration is very short. So currently, currently in the desalination sector, because of the low capex and opex of seawater reverse osmosis, it has eclipsed the thermal technology and dominates the desalination sector. In Indian SWRO plants, 75% of the O&M cost is contributed by the power cost. You can see in the figure in the right side. And worldwide, many attempts are successfully being made to minimize the specific power consumption and reducing the power cost to bring down the desalinated water cost. In the world's largest desalination market, which I call it as a Gulf region, desalinated water price have largely hovered in the range of 0.4 to 0.55 US dollars. Hassan IWP in Dubai, which was awarded to Aqua Power bidding team at a levelized water cost of 0.37 US dollars per meter cube. However, these prices are based on the RO process energy consumption of around 2 kilowatt hour per meter cube, and also the electricity cost in Middle East is much lower than Indian water cost. However, these prices are based on the RO process energy consumption of 2 kilowatt hour per meter cube. There may be some plants which are operating at a higher kilowatt rating depending upon the type of energy recovery devices and the membranes available there. The theoretical minimum energy for desalination of a seawater with a salinity of 35,000 milligrams per liter is approximately 1.07 kilowatt hour per meter cube at a 50% recovery. Nevertheless, the practical thermodynamic limit of seawater reverse osmosis in terms of specific power consumption is about 1.6 kilowatt hour per meter cube for desalting seawater of 35,000 ppm with 50% recovery. Hence, still there is a margin to squeeze in the specific power consumption of the desalination process. There are a lot of innovative ways to reduce the energy consumption of SWRO process. First one is improvements and developments of the RO membranes. New RO membranes are being developed, which will have a higher flux at a given pressures. Higher flux means higher flow, that is, or higher permeate protection in a given area. So aquaporin is developing new membranes. There are carbon nanotube membranes are there. This membrane at a given pressure, that is current operating pressure, they can produce more permeate. And there are other research and development processes are going on simultaneously at many locations. Improvements in efficiency of all energy consuming equipment is also attempted simultaneously by going in for higher capacity units. Higher efficiency pumps are brought in, higher efficiency energy recovery devices. The one yellow what you see here is a pressure exchanger made by ERI, Energy Recovery Integrated, which has got efficiency of close to 97 to 98% when compared to the Pelton wheel, which is shown slightly above that with a blue color, which had an efficiency of around 85 to 86% efficiency. So because of that, and on the right side, you can see a turbocharger which had an efficiency of 88%. So continuously, there were developments going on in energy recovery device to recover the brain energy getting wasted. Then there is high flex membranes operating at low pressure. Because of that, the more permeate production was there for a given bar pressure. Introduction of new configuration and membranes also to improve the quality and energy efficiency was done simultaneously. Hybrid membrane arrangements in the pressure vessel is being now attempted in most of the plants. It means that first few elements, there will be a pressure vessel in which 7 membranes are arranged. First few membranes, that is 4 or 5 membranes, will be high salt rejection membranes, and last 2 membranes will be high flux membranes, so that there is a compromise made between the salt rejection and the energy recovery to have an optimum efficiency of operation. Then there is a pressure center design. In normal RO plants, what we have is each RO train will have a high pressure pump, energy recovery device, and a booster pump and the membrane arrangement. Whereas in the pressure center design, all high pressure pumps are joined together in a common place, and all booster pumps are joined together at one place, and energy recovery devices are commonly placed, so that the size of the pumps are big, and we can go to an efficiency of around 90 to 91%, so that the specific power consumption can come down. This is already tried in some of the plants in Israel. And elimination of brake tank, we call it as inline design, where there will not be any brake tank between the pre-treatment system and the RO system. Because of that, there will not be any energy loss, which improves the specific power consumption of the plant. Reduction of additional energy consumption by mitigating the membrane fouling. In RO plants, major problem is membrane fouling or scaling, which can increase the pressure, and because of that, the power consumption will become high. Introduction of DAF, dissolved air flotation system, biocide dosing to take care of the biofouling, and use of low fouling membranes has brought down this energy consumption to a greater extent in the modern plants. Then optimizing the power, chemical consumption, manpower, resources allocation, etc. with artificial intelligence and digital twinning has also considerably reduced the energy consumption in the RO plants. I just wanted to bring here a breakthrough which has happened recently in the desalination, which is a new concept. MIT scientists have discovered an astonishing phenomena called photomolecular effect, where light can directly cause water to evaporate without the need for heat, potentially leading to significant increase in evaporation rates compared to the traditional methods relying solely on heat. This breaks the thermodynamic barrier in the thermal desalination plants. We have to wait and watch how this is going to take shape. Then, by byproducts are a down the stream integration with green hydrogen production, mineral mining from desal plants also are going to make this SWRO plant water production costs more attractive. Predictive maintenance with AI. AI is being used to predict equipment failures and maintenance need in O&M projects. By analyzing the historical data and the real-time sensing informations, AI algorithms can identify the potential issues before they occur, reducing the downtime and optimizing the asset performance. See, in these plants, reducing the downtime has a great advantage because every time the plant is shut down and started up, we have loss of energy and loss of production. So if a plant can run without any downtime, that means its plant load factor becomes higher and the operating cost comes down. Optimizing the resources also by AI has had given a good leverage. AI-driven optimization algorithms are used to allocate resources efficiently in EPC and O&M projects. This includes workforce scheduling, equipment utilization, material management, leading to cost saving and improving the project timeline. So project timeline saving is also a saving in the manpower cost, saving in the project cost. So it results in a lot of saving. So the capex comes down with use of AI to optimize the resources. Twinning and simulation. See, because of the twinning in EPC or O&M projects, creative visualization and replicas of the physical assets are taking place, and experts are able to guide and control. Because of that, decision making is more efficiently done, and performance optimization can be effected efficiently. Another main attempt which is being made is to reducing the energy cost. Maybe you will be able to recall what I told, that 75% of SWRO O&M cost is in power consumption and power cost. So most of the desalination plants worldwide are supplied power generated from fossil fuels, and the power tariff are very high. So if we can go in for a cheap renewable power alternatives like solar energy or wind energy, which is successfully implemented in some of the desalination plant, will drive the O&M costs downwards considerably and reducing the power tariff. Al Khabji in Saudi Arabia has a solar SWRO plant with a capacity of around 60,000 meter cube per day, which is currently the largest solar desalination plant now. Innumerable developments are taking place in desalination technology to bring down the lifetime water cost of the desalination plants. Some of the important developments are listed below. One is forward osmosis. The other one is membrane distillation process, vibration shear enhanced process, capacitive deionization process, humidification dehumidification process, promising new RO membrane developments. So because of the paucity of time, I'll explain few of them so that some of the interesting features can be known to the audience. Forward osmosis. This is an osmotic process. It uses semi-permeable membrane to separate the salt from water. It uses the osmotic pressure gradient instead of hydraulic pressure gradient, which is used in the RO plants, to create a driving force for water to transport through the membranes. No energy is needed to drive the water flux. In RO plants, we used to use a pressure of around 58 to 60 bar in order to force the water through the fine pores in the RO membranes. Whereas, since it is here in forward osmosis, it is driven by the osmotic pressure gradient. No extra force is required for the water, and the water flux is also higher. It is innovative membrane-based technology. It has a potential to reduce the cost of the plant as well as environmental impacts in the desalination. So it is forward osmosis is nothing but when you separated a feed and brine, you can see that due to the osmotic difference in the gradient, feed water will go towards the brine to dilute it to have equilibrium achieved. So this is forward osmosis. Whereas in reverse osmosis, you apply a force in order to have fine pure water molecules to pass through the semi-permeable membrane and reach to the other side. Actually, in forward osmosis, a concentration solution, which is called draw solution, is the source of driving force for the forward osmosis. Selectively permeable membrane allows passage of water but rejects solid molecules and ions. Osmotic driving force in the forward osmosis can be significantly greater than the hydraulic force driven in the RO process. This results in higher potential flux rates and recovery. The selection of appropriate draw solution is the key factor in the RO performance. The right side picture shows a pilot arrangement for a forward osmosis system. The blue area which is hatched and the lines shows the saline water entering the membranes, and the green area shows the draw solution. So because of the concentration difference, the pure water molecules from the saline water passes through the membrane, try to dilute the draw solution, and this draw solution is taken to another tank from where it is sent to a recovery system where the pure water from the draw solution is separated and taken out. So the process is very simple. It does not need any high pressure pumps in order to drive the process. See, this process has a high osmotic efficiency, and main important is the draw solution should not be toxic, so that even the traces amount that is going into the water that is produced should not affect and it should be acceptable. And the draw solution should be chemically compatible with the membranes that is being used. Some of the draw solutions used are given there: magnesium chloride, calcium chloride also, and even sucrose can be used as a draw solution. Hydration Technology Innovations is a company which produces emergency sugar drink that can be produced from contaminated water simply by placing a pouch fabricated from a selective membrane and permeable membrane in the available water. The sugar solution inside the pouch has a high osmotic pressure, and over time, clean water flows from the contaminated side to the sugar side to produce energy drink. So similarly, there are other innovations also being made using forward osmosis process. One of the plant which is in Oman is a 100 meter cube per day plant. It is built by Modern Water. I'm telling this is the news which is 10-12 years old, where the plant was operating and producing potable water. Comparing this forward osmosis to established technology, I'm listing down some of the potential advantages. It operates around 1 atmospheric pressure when compared to 60 atmospheric pressure, which is there in the reverse osmosis process. And membrane compaction is not there because the pressure is very low, and less fouling propensity compared to the RO plants. These are the selected advantages. But there is a limitation in the draw solution, and the following advancements need to be considered for the technology to be brought into full-scale operations. Identifying the effect and economical draw solution and technological approach that removes draw solution economically, because water has to be removed from the draw solution, separated efficiently and at a low cost. That is a very important thing to make this process successful. And developing a new and additional membrane source, because currently limited membranes are only commercially available to be used as a forward osmosis membrane. One is a cellulose triacetate membrane, which is made by Hydronautics company, is currently being used. Addressing mass transfer limitations resulting from concentration polarization within the membrane support layer also needs to be studied, and it has to be improved. And developing, currently there are not much new modules available, so developing new modules suitable for the full scale implementation is also equally important. The next process is membrane distillation process, which is gaining a lot of importance nowadays. Membrane distillation process combines the membrane technology and evaporation process in the single unit. The appeal of MD is that it functions at atmospheric pressure, once again similar to forward osmosis, and requires only low feed temperatures, 70 to 90 degrees, which is possible by means of a solar energy or waste heat usage. MD transport water vapor through pores of hydrophobic membranes. See, the membranes used in RO process are hydrophilic membranes, whereas the membranes used in MD process are hydrophobic membranes. Because of that, water does not stick to the membranes, only vapor passes through due to the temperature difference across the membranes. The membrane allows the water vapor to penetrate through the hydrophobic membrane surface while repelling the liquid. The clear vapor is carried from the membrane and condensate produces a pure water. This is a typical plant membrane idea that is given here. Hot water flows on one side and the condensate flows on other side, and the condensate is cooled by means of a cold water. The driving force of the MD is partial vapor pressure difference between the hot side and the cold side of the hydrophobic membranes. Pressure on the cold side can be reduced by sweeping gas or vacuum arrangement. A variety of methods have been already employed and tried. The process shows the process. The slide shows the process flow diagram of a pilot plant, which where I have tried already and found successful. The blue side is the cold side and the red side is the hot side, and the vapor from the blue side passes through the membrane, and the vapor from the red side passes through the membrane and goes to the blue side, where it is cooled and then it is collected as water. So here the main advantage is it can be used for very high concentration also, which we can see in next slide. This is the membrane distillation process pilot test which was conducted, and the curve shows, you can see the concentration we gradually increase. The blue line is the concentration of the feed side. You can see that it goes up to 250,000 ppm, microsiemens, and whereas you can see that the bottom line, which is indicated, it shows a stable, very low TDS, which was always below 100 milligrams per liter. Once again, here also we are giving comparison to the established technologies. The ability is there to use low grade heat, solar or waste heat, whatever it is there. And because the temperature required is in the range of 70 to 90 degrees, less organically fouling propensity compared to RO. RO main problem is organic fouling or biofouling that is happening, since it is these membranes are hydrophobic, the possibility of organic fouling and biofouling is comparatively less. Also, pre-treatment requirement required for this process is not as elaborate as the RO process. Uh, and it can also have the same membrane process. You can see, you saw in the previous curve that the water produced has got a stable TDS irrespective of the feed water quality change or TDS change. You can see that it went up to 250,000 microsiemens and still the outlet water was less than 200 microsiemens. So MD membranes are more chemically inert and resistant to oxidation than traditional RO, because RO membranes are can be easily oxidized by passing through a chlorine or chlorine dioxide. And so because of that, we need to be very careful, and the feed water which is admitted into RO plant is dechlorinated before admitting into the RO membranes, whereas this is not the critical case with the MD plant, because membranes used are more tougher. Teflon or other types of membranes are used when compared to RO and NF process, and produces high quality water than NF, RO, and IDR or any CD process. It has got still under, it is to be still underdeveloped, and knowledge about the following has not been established, like treatment efficiency of large scale installations and the economics of it is to be established. Uh, we need special hydrophobic membranes. Existing commercially available RO membranes are not suitable for this MD application because of such membranes have relatively low product water flux, whereas these alternative, if you see RO membranes, there are several manufacturers available, like Hydronautics is available. Then you have DuPont, you have then Toyogo or Triflex. There are many membrane Toyogo. There are many membrane manufacturers available to supply the membranes, whereas such in commercially in large quantity also they can supply, whereas in MD process we don't have such facilities. So still MD has to go a lot of optimization process, and since to have a low specific power consumption, you have to have a multiple stages. So that will require a larger footprint and for a given equal capacity. Contamination of distillate can occur when the membrane fouls and wets the membrane surface, because the advantage is only hydrophobicity of the membranes helps. So when membranes get wet, it can pass some of the water molecules also. Use of multiple stages can reduce the energy requirement but increases the capital cost. There are different types of MD process: direct contact membrane distillation, air gap membrane distillation, sweeping gas membrane distillation, and vacuum membrane distillation process. And based on this forward osmosis or retarded osmosis, membrane-based concentration process is developed based on this forward osmosis process. This is called osmotically assisted reverse osmosis process, in which RO brine can be taken through different stages of ORA process, where the salinity of the water that is going out is reduced, and it increases the salinity of the water that is flowing out to concentrate it. So the brine concentration of up to 200,000 ppm can be achieved. Based on this technology, a big plant has been built in Indonesia, and it is producing salt. So this completes my section. Thank you for attention.
So thank you so much for that enriching talk. That was very informative. And now we'll give an opportunity to our participants to engage with our speaker. So if anybody has any questions for Mr. Basha, please unmute yourself and ask your question. So while we're waiting for our participants to respond, there is one mention on the chat which talks essentially about the wastewater generated during desalination. So we would love to hear your insights and your thoughts on this, because the brine management is something that we would like to hear more about.
Yeah, actually, that is coming out of desalination plant. For example, it has a 50% recovery. It will have a double the concentration of seawater that is coming out. So if we discharge directly into the sea, it can affect the marine organism. So modern plants have got a diffuser arrangement at the outfall. So the outfall pipe will be extending up to half a kilometer or 1 kilometer into the sea. At the end of the pipe, there is a diffuser arrangement which can diffuse the seawater and creates diffuse the brine and creates a recirculation and dilutes the water within a short radius of around 30 meters. So the fear of concentrated water spreading out and affecting the marine organism is not there. Also, a lot of research is going on in nowadays in order to have brine mining from this. Lot of salts can be recovered from this, which are very essential things and very expensive, and we can recover the cost through the brine mining process also. If you have gone to recent International Desalination Association conference, there are several papers on this brine mining, and parallel research is going on at many places.
Okay. Thank you for that response, sir. As a follow-up to that, I would like to ask that when you actually do a LCA analysis for any desalination plant, what is the time period that is considered? So even when you're looking at the effect of brine on the marine ecosystem, etc. So what is the time period that a plant should generally look at?
See, actually, first of all, for a reverse osmosis plant, if you wanted to have, you have to have the analysis of seawater, because the design of RO plant depends on the seawater ingredients. What are the constituents? Not only the TDS, the TOC level, that is total organic carbon level, chemically oxygen demand. So there are many factors like heavy metals presence. All these things are very important to know in order to design the RO plant. So at least one season complete water analysis at a certain period has to be done. Second, there is a report has to be generated on environmental impact assessment, and environmental impact mitigation measures are to be made as a report and submitted for environmental ministry clearance. So factory inspectorate clearance, there are many, around 20 such clearances are required. So at least you start at least 2 years before starting any plant, engage a consultant to do the study and prepare the report, submit it, and also land acquiring is another important thing. And selecting a location where the seawater quality is very bad is not desirable, because when the seawater quality is very bad, then the pre-treatment process becomes more elaborate and makes it very costlier, because membrane manufacturers stipulate certain condition for the entry of the seawater into the membranes. To achieve that quality, if the seawater quality that you are receiving is very bad, an elaborate pre-treatment needs to be done. So selection is important. Another thing, if the seawater is very shallow in that region, you have to go very long distance for the intake pipe and the brine outfall pipe, so that you get a required depth required for example, a 100 MLD plant, 100 million liters per day plant requires a depth of around 10 meters. So in some places, the 10 meters can be achieved within 400, 500 meters. In some places, you have to go for to 5 kilometers. So in such cases, any work which is done on marine services is very expensive and costly. So selection of site is also equally important. So there are many such factors which are involved. What is the material of construction you require, depending upon the life, because seawater is corrosive. You have to select material which is less corrosive when it is at high pressure. When it is low pressure, we can use non-metallic components like high density polyethylene, FRP or so things. Whereas when it goes to high pressure like 60 bar, 65 bar, you have to have a metallic, and we go in for super duplex stainless steel, which is 3 to 4 times costlier than stainless steel. So that increases the life of the plant. So life of the plant decides the quality of material required. Similarly, the quality of water, you can make even close to distilled water with a 3-stage RO process. But normal utility water plants use only single stage. So when the water quality requirement is very good for industrial purpose or for electronic industry, where you want 5 microsiemens of water, then you need to go in for 3 stages. So capex will be slightly increased. But however, this will be cheaper than a thermal process, because thermal process produces high quality water. The water coming out will be having a 5 microsiemens per centimeter of conductivity, whereas thermal in desalination plant for drinking water application produces 250 microsiemens in single stage. In second stage, it can produce 20 microsiemens. In third stage, it can produce 5 microsiemens. So multiple stages have to be done. So there are many such factors are involved. So in designing, you have to take care of all those things.
Thank you so much, sir, for sharing your rich experience in the field. And if anybody else has any questions,
I have one question.
okay.
So,
Please.
very nice presentation, sir. Very informative presentation. So actually, I wanted to know the final treated water, is it supplied for drinking purposes, or is it supplied for industrial purposes?
It can be supplied for industrial purpose, as well as it can be supplied for drinking purpose, because the water coming, we call it the permeate water that is produced from the RO membranes, is very pure. That is, it is free from bacteria and virus, and but slightly pH will be lesser than 7. That is slightly acidic in nature. So in order to have it as a drinking water plant, we have to remineralize with calcium to increase its pH level as well as alkalinity, and also we make longitudinal saturation index of water positive, so that it is not corrosive when it passes through steel pipe. So all these things are done in the remineralization process for drinking water application. Whereas for industrial application, we normally have 2-stage process. In first stage, we produce certain quality. It is passed through the second RO plant, where it can produce very high quality water depending upon the industrial requirement, whether you need 100 microsiemens or 20 microsiemens, depending upon the requirement. If it is a power plant, you may require 10 microsiemens. So it is whether 2-stage or 3-stage industrial process, it is decided based on the quality of water required.
Okay, sir. Thank you.
Thank you so much, sir, for answering all those questions. I'll take the liberty to, on behalf of the IWA Young Water Professionals India chapter, to thank you for your time and for being with us today this evening. Thank you very much, sir. We'll now move on to our next speaker. So Dr. Surbhi is our next speaker, a young water professional herself and a project scientist at IIT Jammu. She is an environmental scientist and has completed her PhD from IIT Roorkee. She has served as a postdoctoral researcher at Sejong University in South Korea and has also worked with Terry as an associate fellow. She's currently working as a project scientist with IIT Jammu in the Center of Excellence for Healthcare, Agriculture and Sustainability. Her work focuses majorly on advanced oxidation processes, and I'll let Dr. Surbhi talk more about her work. And thank you so much once again for joining us today and for giving your time to share your experiences with the audience. Over to you, Dr. Surbhi.
Yeah, thank you for the very nice introduction, Akansha. So can you see my slides?
Yes, we can see your slides. If you can just put it on slideshow.
Okay, perfect. Oh, so you can see my slides now, okay, in a slideshow mode. So yeah, so thank you so much for inviting me to this webinar and to talk about this emerging technology. Basically, I'll be talking about advanced oxidation processes, and it was very informative session by Mr. Basha as well, He talked about desalination, which is actually, a very good technology which will help as a developing economy for building a very good water infrastructure in our country. So I'll be talking about the advanced form of treatment that will be majorly for wastewater treatment, that is advanced oxidation processes, and why there is need to focus on such kind of emerging or advanced technologies. Although I believe there is nothing advanced, this is the need of the hour. We need to focus on such kind of technologies because right now we are not dealing with the sewage, we are dealing with the urban sewage when we talk about the wastewater. So yeah, so just to start with my brief introduction, actually it is covered by Akansha, so I'll not go into that. I'm also serving as co-chair for IWA, this Advanced Oxidation Processes Specialist Group. So apart from that, that is the additional thing that I would like to add upon. So yeah, I can't move the slides. Yeah. So yeah. So as I was telling, why there's need to focus on these advanced technologies and what we should know, what are the emerging problems in the water sector. So I'll believe there are two set of problems that we are dealing with right now. What is first is emerging contaminants, or we can say micropollutants or microcontaminants. These majorly involve pesticides, pharmaceuticals, day-to-day products that we use in our lives, personal care products, and all these products have shown to be very creating many public hazards in if they are consumed on day-to-day basis, if they come into our taps, which is the case right now. And second will be the disinfection byproduct. Why it is important to focus on this class as well, although I believe it is also part of emerging contaminant only. So disinfection byproducts are the products that are formed in the treatment plant itself. So for example, in India, we majorly use chlorine. So this chlorine, when this chlorine reacts with the organic matter that is present in the water, it leads to the formation of these disinfection byproducts or trihalomethanes or haloacetic acids, haloacetonitrile. And these are possible human carcinogen. And the thing with this set of contaminant is that disinfection occurs at the end of the treatment chain. So it will come into our system if it is not combated there, if it is not treated there. So these are two sets of problem that actually require advanced kind of treatments, and advanced oxidation processes are actually a way to go. They can actually solve our three sets of problem, I'll say, because as a developing economy in the water sector also, I'll say we are dealing with the conventional set of parameters, which are BOD, COD, organic pathogens that we are dealing with. And then these two sets came. And the current set of system that we are using, that is the primary, secondary, tertiary, we all know about it, the conventional form of treatment, be it a drinking water treatment plant or a wastewater treatment plant, or for say industrial water treatment plant, they are not designed to treat these contaminants. And for that matter, we are not focusing on acknowledging their presence in the environment, which is actually the need of the hour, that we need to focus and acknowledge their presence in our environment. So yeah, apart from the conventional set of problems, these two set of problems can also be combated by the advanced oxidation technologies. So now, okay. Yeah. So now when I say we are not dealing with the sewage, we are dealing with the urban sewage. And why we call it urban sewage? Because apart from the normal water quality parameters that we are focusing upon, there are another set of these contaminants that are continuously emerging, like pharmaceuticals, these antibiotics that we are taking on day-to-day basis. They are going undigested from our system and making their way into these wastewater treatment plants. And these treatment plants are not designed to focus or treat or remove these contaminants, though, so they will eventually make their way back into our houses. So it can actually be a very, enormous public health hazard. So there's need to focus on that. Now, when I say this cycle can be called as a wastewater treatment cycle, just like a water cycle, and pollution that has not been, focused upon it at any point of the system will eventually create many problems. So there is need to focus on each and every kind of treatment system. So for example, first water treatment plant, they are designed to treat organics and pathogen, but not ECs. Similarly, wastewater treatment plant, they are designed to treat complex organics, nutrient pathogens, but not ECs. Similarly, with the effluent treatment plant, they are also not designed to treat ECs. And eventually they will, the final effluent from these wastewater treatment plant goes to surface water. And this surface water is the influent to these treatment plants, water treatment plants. And if they are not treated there, they will certainly be present in our glass of water at our homes. So that is why we need to focus on such kind of advanced oxidation technologies. So now having said that, this is why we need to focus on such kind of technologies. I'll also briefly talk about what we already know. So we know there's a domestic wastewater treatment, there's industrial wastewater treatment. But the thing is, as per CPCB, India's 70% of water is untreated. That is, it is going as it is in the surface water bodies. So when I said we are facing three set of problems, two being the emerging problems, first being the conventional problem. This is that problem that 70% of India's water treatment infrastructure is yet to be made. But when I say that it is a problem, I'll also say that it is an opportunity in disguise. And by saying that, what I meant is, when we are going ahead with building our water infrastructure, why not include the advanced form of treatment here only, so that after 10 years we will not suffer the problem of ECs. And if the problem is only of conventional water quality parameters and not of ECs, it will actually be a very problematic state in the coming years. It will not include ECs in our treatment systems. So that is why I said three set of problems needs to be combated here. So now this is the primary, secondary, tertiary form of treatment, the wastewater, the normal conventional wastewater treatment. So my solution is either for the 70% of the plants that are yet to made, have an advanced oxidation based system, entirely new advanced oxidation based system. And if not, if there are existing plant, we can have them retrofitted. We can have these advanced oxidation based technologies integrated at particular stages, so that these ECs will not be released into the aquatic environment. So the 30% that are already existing can have retrofitting, can have these AOPs integrated in their system, and the 70% that is yet to be built can be entirely AOP based system as well, because these AOPs will not only treat the water in terms of conventional parameters, it will focus on ECs as well. It will focus on the disinfection part as well, because AOP is in itself a disinfection method also. So that is my proposal for actually what I'm working upon, to have AOP as an integrated method, or to have AOP as a standalone method for the water treatment, for the wastewater treatment industry. So now, why advanced oxidation processes, and what actually is advanced oxidation? So any method that generates hydroxyl radical, majorly there are ozonation based methods, hydrogen peroxide or UV hydrogen peroxide, and there are many more methods that can generate these hydroxyl radicals. And why these hydroxyl radicals are better than other forms of oxidizing agent? Because they are non-selective in nature. That is, this similar technology, same technology, can be used for variety of compounds, variety of these chemical compounds that we want to target upon. And what this AOP does is, what this hydroxyl radical does is, it converts higher molecular compounds into lower molecular compounds. And what you can do is, you can combine this advanced oxidation with the other form of treatment method that I have done in my research. Is I have combined advanced oxidation with the biofiltration to make it more cost effective, and overall to make it chemical free as well. So that is why it is advantageous over other forms of advanced treatment methods. So I'll just give a brief about what I have done using advanced oxidation processes. So I focused on disinfection byproducts. So it was actually first study in the country which analyzed THM in wastewater treatment plants as well as in drinking water treatment plants. So we used GCMS and everything, and we got to know the presence of THMs there. And there's very actually interesting fact to share also that when I started working on THMs, the maximum contaminant level, the permissible level for these THMs was around 100 ppb in US. And when I completed my this research, it was 60 ppb. It has been reduced to 60 ppb, but we are still at 460 ppb. So there's need to actually revise those guideline values also. So coming back to AOPs, so I screened 3 AOPs, ozone, UV peroxide, and ozone peroxide. And I saw the maximum degradation in all the 3 AOPs. So yeah, these were the results. So when we talk about AOPs, we were concerned about the maximum degradation. So maximum reduction was achieved in the case of, I guess, UVH2O2 when we talk about only AOPs, not the AOP BSE entire process. So this idea came later on in our study that why not combine it with the biofiltration and make the cost more effective, because whenever we talk about AOPs, cost is the first factor that comes into picture, that it is costly. But you combine it with biofiltration, it will be cost effective, it will be cheaper than other forms of method that we are using for wastewater treatment these days. So yeah, for when we screened these AOPs, UVH2O2 was the best AOP among the all. It reduced hydrophobicity. Actually, all AOPs performed better, but UVH2O2 was the one which performed better in terms of THM forming potential. THM forming potential was reduced up to 90% in case of UVH2O2 treatment. Then we combined this selected AOPs with the biofilter, that is the biological activated carbon filter. We made this biological filter from scratch. We ran past the influent this water through the granular activated carbon, and this converted it into this BAC. It took us around 90 days. So it was made from scratch actually. And then we passed our AOP treated water through this. But the thing here is that when you combine AOP with the BAC, you need to focus on biodegradability, because the microbes play a very important role in the biofilter. And you need to make sure that whatever contaminant you want to get treated should be used by microbes, should be good enough to be used as a substrate by the microbes. So there we tested for the biodegradability, biodegradable DOC. And while testing in case of all 3 AOPs, it was seen that the maximum biodegradability was achieved in case of O3H2O2 treatment. So we went ahead with that. And the final outcome of the study was that ozone, if combined with the peroxide, will give better results along with the biofiltration. So the impact and outcome of this study was that this technology is much cleaner, much greener, and it produced very high quality water that is free from ECs. Its efficiency is high, it is scalable, it is modular, and if there is an existing treatment plant, it can be retrofitted there. And if we want to build a new treatment plant, the same technology can be used entirely there. And this technology can be used for sewage treatment plants, drinking water treatment plants, and even for the effluent treatment plants as well. And this technology is actually being used at a pilot scale at IIT Roorkee treatment plant also. So yeah, so this is actually picture of Mr. Bill Gates, who is drinking the treated water. They have their patented technology. They are converting this wastewater into drinking water. So there's no such thing as waste, only a wasted resource. So we also have a conference in April this year. So deadline for poster submissions is 7th March. So any of you is interested can submit the posters there. So yeah, that's it for my presentation. Yeah.
Thank you so much, Surbhi, for that very informative presentation. With that, I open it up for questions. If anybody in the audience has any questions, please unmute yourself and ask the speaker your questions. Vatsal has a question there. So Vatsal, can you please unmute yourself and ask your question?
Yeah. Uh, Mrs. Surbi, it was a very good presentation. For
Thank
me,
you.
you told that from wastewater treatment you make drinking water, but the TDS of that water will be 850, 900 because wastewater comes with that TDS and you are not rejecting salt anywhere. So you will have that high TDS water which cannot be used for drinking application. This
So,
is
but
one.
yes,
Okay.
yes, yes. For the
Okay.
TDS part, if you talk about industries, so our suggestion is to use it after the evaporators that MES and everything that they are already using have AOP after that, because our problem is emerging contaminant, these micro contaminant that should not come into the aquatic systems.
Okay, the one more thing is it's improvements which I am suggesting. Actually, we have designed TTRO plants, tertiary treated RO plant, which
Okay.
takes secondary treated water from the wastewater treatment plants, and we out of that we produce industrial water, which is we convert 80% of the water to the industrial water, and we have only remaining 20%. So for you, when you have a TTRO plant, the water to be treated becomes 20% instead of treating the 100% water.
Right, right, right.
So that's just a suggestion from me.
Yeah, it's actually a very, very good, informative point, actually.
Thank you.
So, Surbhi, we also had one question during our registrations, and this could be open to both the speakers as well. So, the question was pertaining while we are looking at these advanced technologies in water treatment, what would you suggest? Like, how do you see these in a landscape like a rural landscape, right? So, rural landscape where water is still a very precious resource in terms of availability. How would you extrapolate these technologies in rural settings?
See, if we talk about advanced oxidation processes, see, the source of water is same for everyone. So even if it is groundwater, even if it is surface water, so we are talking about the entire water ecosystem, water cycle. So it is not about urban or rural. Somehow, if at any point these contaminants or pollution will make their way into, these surface water bodies. So I'm getting the sense that, if you talk about rural population, you talk about that, cost and everything. But if we don't go into that side, the focus is on emerging contaminants and the emerging kind of these pollutants that are making their way into every set of this water arena. Yeah.
Seawater reverse osmosis plant is mostly suitable for coastal region, whereas in inland plants we have a brackish water treatment system, but the major problem is brine disposal. So the brine that is coming out of the plant needs to be disposed. So industries can have a zero discharge arrangement where the brine can be further concentrated, water can be produced, and salt can be produced out of it. But the process becomes very expensive. So only industries can afford to do that. For domestic, for the water treatment and other things, it is very difficult with the RO system.
True. Thank you so much for those inputs. We have one question for Dr. Surbhi by Mr. Shiv Kumar asks, what is the potential of nature-based solutions to reduce emerging contaminants?
Yes, like I mentioned that biofilters that I have used in my study. So they are actually a very, very nature-based solutions or any kind of solutions that are, so sort of eco-friendly, we can say. They're actually very, very good way to go. because these microbes, see the wastewater treatment plant that are designed on the concept of microbes that are already present in the water. If you read Metcalfe Eddy, their first line is that we have taken this solution from the nature itself. The microbes that are present in the water, they have capacity to purify water. Like River Ganga, we say that it has a very high self purification capacity. That is the thing we have taken from the nature itself. So yes, nature based solutions are actually very are way to go. They can actually be used for treating these emerging contaminants.
Perfect. Thank you so much for those inputs. And if we don't have any further questions, I'll hand it over to Danish to give the final vote of thanks to both our speakers. And thank you so much from my end for being part of our session.
Thank you, Akansha. Thank you. Myself, Danish. I'm the chair of IWA-YWP India chapter. I also a senior project scientist at IIT Madras. It was a very insightful and engaging webinar on emerging technologies in water treatment as well as the wastewater treatment. I believe all the participants would have had a very insightful experience and knowledge sharing from the speakers. First and foremost, I thank the speakers, Mr. Amit Basha and Dr. Surabhi, taking their time, valuable time, accepting as a speaker for this webinar and giving your insights on your experience. And I deeply also thank all the participants who are there during this time, taking your time and giving importance to this webinar and knowledge sharing. And finally, not but not the least, I thank Akansha and Abhijit taking most of the time and scheduling this webinar. And I also thank all the other IWA, YWP steering committee members for their efforts. Yeah, thank you. And dear participants, we would love to hear from you. You can give some suggestions if there are something from the emails that you have received. And if there are some important topics that you would like to hear from us, please share it. We will definitely arrange something which is very much valuable in the water sector. So we are looking forward to have multiple sessions similar to this on the coming months. Yeah. Thank you so much. Yes, please, Akansha.
Thank you. Thank you, Mr. Basha. Thank you, Dr. Surbi. Thank you so much.
Thank you. Thank you for inviting us.
Yes, thanks.